Greetings. In the previous video, we managed to define our problem, and it concerned a cylinder which was divided into two parts with a piston. When the pin was removed, the piston could move freely, no friction. This movement was only a function of the pressure difference at its two sides. At the same time, the piston was a good conductor, and eventually we expected the temperature on the two sides would equal. So we had the initial conditions, we had the final conditions. At least we knew that they were equal, the properties were equal, and also we managed to simplify the governing equations for A, B, and A and B together. Now, what we do now is to move to another step in our usual process for solving problems, and that is we do find the properties. Well, it's air, so it's perfect gas. What we could do is to write down the perfect gas law and try to find properties. We have two independent properties to start with, and therefore we should be able to find the rest. The perfect gas law is PV equals mRT, or we may write it as PV equals RT. PV equals RT. Now, let's since we have volume, using this version would be to our benefit. So what I do is that for writing this equation for A, what I do is that MA would equal PV divided by RT, and that's what happens in A. P is 200 kilopascals times V, which is 1 cubic meters, and divided by R, which is 0.287 kilojoules per kilograms Kelvin for air, and times temperature, which is 300 kelvins. And the outcome would give us the mass in A, initial mass in A, which is 2.323 kilograms. This is the initial mass in A, and if I had done a similar practice with this equation, I would have calculated VA1, which is 0.4305 cubic meters per kilograms. That's as simple to divide V by M, and you will get the same answer. As for B, we may repeat the same practice with the knowledge of pressure and temperature and calculate both mass and specific volume. So MB would equal 1000 initial pressure times 1, which is its volume, and divided by 0.287 kilojoules by kilogram Kelvin, and times 1000, and that is 3.484 kilograms. That is mass in B. And if we repeat the same practice with this equation, VB1, specific volume, would be 0.2870 cubic meters per kilograms, and therefore we have both mass in initial mass and specific volume for A and B. We now know that M2A equals M1A, and therefore MA, which we use here, is 2.323 2.323 kilograms for both of them, and therefore we know this value here. So we now know MA, which is this value. CV0, well, we could read it from the tables, that's no problem. T1A we know, and there is no way we could know Q or W in this process. We don't have any means for that. As far as B is concerned, we know MB, we know CV0, and we know T1B, and we don't know heat transfer or work in these two equations. So here we have T2B, which is equals T1B, and we don't know it yet. Now, let's move to this equation. We know M2A plus M2B, which is, and we know M1A and M1B. This is 2.323, 2.323 plus 3.484, 3.484, and the outcome would be the sum for these two, because these two terms in brackets are equal, and the total of MA plus MB would be 5.807. That would be the total mass in both A and B, which doesn't change through this process. Now, we know here we should simplify this equation just to get to a better position for calculating the temperature. Let's see what we can do with first law of thermodynamics. I should follow a very similar practice as I have done here, just to bring this equation into a shape like this one. What I should do is I should write it as follows. For I should combine these two terms, okay, and these two terms. So I could write MB times U2B minus U1B, which is this term minus this one, plus MA times U2A minus U1A, U2A minus U1A, and that equals 0. A further move in this direction is to simplify it further. MB times CV0 times T2B minus T1B plus MA times CV0 times T2A minus T1A equals 0. And in this equation, what do we have? We have MB and MA. We both are known. We have calculated them up there. Also, we have CV0 in both cases. That's the same, and you could read them from the tables. T1b and T1a are known. That's a good point. So the only unknowns are T2b and T2a, which are the final temperature on both of the piston, and we know that they are equal. This is another equation that we have. T2b equals T2a. The final temperatures on both A and B are the same. So all we could do is to put numbers to this equation, and MB is 3.484 times 0.717 times T2. I would write it T2 just to simplify it for both A and B, which is the same. T2 minus T1B, which is 1000, plus MA. MA is 2.323, 2.323, and times 0.717, which is CV0, times T2 minus T1A, and T1A is 300 kelvin, and that equals 0. Calculating this equation would result in T2 equals 720 kelvin, which is the final temperature in both A and B. The knowledge of the final temperature in both A and B could give us the final pressure and the final volume in both A and B. This part, what I would do is to just take them all as a whole, because in fact A and B, when the piston takes no pressure or no temperature difference, we could take all A and B as the same cylinder. PV equals mRT, and that results in P equals overall mass, the total mass, which is 5.807. This is the sum of mass in A and B, as we just calculated and wrote it down, times R, which is 0.287 kilojoules per kilograms Kelvin, times the final temperature, which is 720 kelvins, and divided by the total volume, which is 2 cubic meters, and that would result in 600 kilopascals. Well, while we know both temperatures are the same and they are 600 kilopascals, we could easily calculate the volume on each side, which has now changed, still from the perfect gas law, because VA, still I'm using this equation, VA equals 2.323, which is mass, times 0.287 times temperature, which is 720, and divided by the final pressure, which is 600. And the outcome is 0.799 cubic meters. At the same time, VB is 3.484 times 0.287 times 720 and divided by 600, which is 1.198 cubic meters. What's happening, in fact, is that at the final condition, V2 is the same. V2 equals the total volume, which is 2 cubic meters, divided by the total mass, which is 5.807, and V2 would be 0.344 cubic meters per kilograms. So we could have as well calculated VA as 2.323 times 0.344, and that would also equal 0.799 cubic meters, and VB as 3.484 times 0.344, and that would be 1.198 cubic meters. So we have both volumes, and as we expected, since both the pressure and temperature was higher in B, therefore the piston has moved to the left. The volume in A has become smaller, and the volume in B is larger. Now, we have done two parts. What is remaining is the drawing of the diagram, and also see what has happened between the two sections in my next video. Thanks for watching, and cheers.